I'm going to be talking about suspensions of swimmers. These are microscopic swimmers, as you'll see. And I'm going to be talking about the impact of hydrodynamic interactions between the swimmers on the velocity fluctuations and therefore the tracer diffusivities. I don't think I'll get to the rheology part, but I don't have much to say at this point, but we'll see. So the work is by two PhD students, Sankalp Nambiar and Piyush Garg. Piyush Garg is in the audience, and he has a poster on run and tumble swimmers. Okay, so I'll first introduce you to what a single swimmer does, and before moving on to a suspension of such swimmers. Okay, and then the talk will be in two parts. The first part where I analyze velocity fluctuations and tracer diffusivities by looking at the microscopic scale. So looking at how a tracer bead interacts with the swimmer, which is how you normally go about things in suspensions at the level of the swimmer or particle. Okay, and then explain some of the findings, especially in simulations. But then I'll go to part two and try to do the same thing from a continuum field perspective. And the reason is that the continuum field approach is more powerful, and it allows you to answer questions that cannot be answered in using the microstructural approach. In particular, a question that pertains to these suspensions of swimmers. Okay. So this is the suspension of swimmers. So this is an example of a bacterial suspension. A bacterial suspension is one of the many realizations of what's known as active matter. Okay. There are many examples, including cytoskeleton, actin, myosin systems, and so on. And if you don't care about the Reynolds number or fluid mechanics, then the amount of things that can come under active matter is only limited by your imagination. So this is the particular system that I'm going to be talking about, because there have been several simulations and experiments on this. So the swimmer is E. coli, and that there is the E. coli. So it's about 10 microns long, quite slender. It has a spheroidal head with a helical flagellar bundle. So E. coli swims by turning that bundle at a given rate, about 100 hertz. And the interesting thing is that it swims, but doesn't swim quite in a straight line. So this is what it does. So the bundle rotates, and the E. coli swims for a certain duration. But then intermittently, one of the motors driving the many flagella reverse direction, and the flagella come apart. Okay, and they point in random directions, and as a consequence, even though they're turning, the bacteria doesn't move in a given direction. It just twiddles for a very short time. That event is called the tumble. And then the motors switch back, the bundle forms again, and it runs in a different direction. Okay, so this is E. coli exhibiting run and tumble dynamics. Okay, the runs last anywhere between 1 to 5 seconds. The tumbles are much shorter, about a tenth of a second, and therefore are more or less instantaneous. So it runs, changes direction, runs, and again. So on larger length scales, it's going to sample its environment in a diffusive manner. Okay. Okay, so relevant dimensionless parameter characterizing this motion is the persistence. So that's the ratio of the run length or the mean free path, which is u tau, where u is the swimming speed, tau is the interval between tumbles, to the length of the swimmer. And notice that this is the length. So I'm assuming they're very slender bodies. Okay. And so the dominant dimension is the longest one. And so for wild type swimmers, this is typically 1 to 5 or so. Although in simulations, some of which I'll be talking about, they tend to be quite large because they neglect tumbling, and the only reason orientation changes is because of hydrodynamic interactions. Okay. So this is, if you want to write down a kinetic equation for the probability density governing run and tumble dynamics, that's the equation. So the omega 1 is a function of the position orientation of the swimmer and time. It evolves due to swimming. It moves. It's convected with the swimming velocity. And there would be an additional term if there is a flow, either imposed or due to other swimmers. The swimmer has an orientation. It's going to be turned by the velocity gradient, either imposed or due to other swimmers. And that there is the relaxation due to tumbling. Okay, so there's two terms. The probability density decreases exponentially. So in a given orientation interval, it decreases exponentially because the bacterium tumbles out of that interval. Okay, but then there is another term which corresponds to bacteria from other orientations tumbling into the interval. And the combination causes the omega 1 to relax to isotropy in the absence of other influences on a time scale of order tau. So tau is the interval, mean interval between tumbles. And so what I'm going to be talking about has this equation underlying everything combined with the fluid motion induced by the Stokes equation. So these swimmers are small, so their Reynolds number is 0. Okay. So this slide is just to tell you that E. coli is not the only organism which does this. There are several other organisms which perform run and tumble dynamics in some version. Okay. So while the swimmer moves, it also pushes the fluid around it, and that's why the different swimmers interact. So we need to have some idea of what this velocity field looks like. So remember, this is the E. coli, that's the helical bundle, which pushes fluid behind as the swimmer moves forward. So you can imagine that the bundle exerts a force opposite to the direction of swimming, while the head drags the fluid in the same direction. So the simplest description of such a swimmer on large length scales would be a pair of equal and opposite forces, or a force dipole. Okay? So that would mean that if you were to consider the velocity field, then the velocity field due to this swimmer in large length scales decays like 1 by r squared. Okay? So they are force dipoles. And E. coli pushes the fluid behind, and so it's termed a pusher. There are other swimmers like algae which execute a low Reynolds version of the breaststroke motion, so they pull in fluid from the front. So they're again force dipoles, but with the two forces directed inward along the swimming axis. Okay? But in both cases, the velocity field is order 1 by r squared. Bacteria are typically pushers, algae are typically pullers. Okay? Okay, so that's what we need to know about the single swimmer. And now we'll go to a swimmer suspension. Okay? So the swimmer suspensions have been probed by putting in micron-sized beads and monitoring their mean square displacements and therefore their tracer diffusivities. This is one of the earliest experiments by Wu and Lipschaber, where they showed that nearly non-Brownian beads in a bacterial bath have diffusivities that far exceed their Brownian diffusivities. Okay, so that was indication that there's some kind of enhanced velocity fluctuations going on in the bacterial bath. And then you have many simulations. Okay, so I'm going to discuss a couple of these in sequence. So the first simulation is by Pat Underhill and Mike Graham in 2011. So I'll just explain to you what this plot is. Okay, so they plotted the velocity variance as a function of the simulation box size. Okay, so that's the velocity covariance there. So what's being plotted is corresponding to r equals 0. Okay, the distance between the two bacteria. So there are two terms here. C is the volume fraction. So the linear term in C corresponds to the velocity variance or covariance in a dilute suspension of swimmers that don't interact. Okay? And this is the interaction term, which is order c squared, so it corresponds to pair interactions. And what they managed to extract in their simulations is the f of r as a function of the interswimmer separation, and what's being plotted is f of 0. So it's the contribution to the velocity variance as a consequence of swimmer interactions. Okay? And the interesting thing is they found that the interaction contribution seems to grow logarithmically with box size. Okay? So this is one of the things that I'll start out explaining. Okay? And then the next pair of simulations that I want to focus on are these. Okay? And so in both these cases, you plot the tracer diffusivity as a function of either the swimmer concentration here or the persistence, which is u tau by L here. So there are two curves here. The red curve here is the tracer diffusivity in a suspension of pushers, and the blue curve is tracer diffusivity in a suspension of pullers. Okay? And you can see that they're almost the same in dilute non-persistent limit, and then they start to bifurcate, okay, which is a consequence of interactions. And the same thing happens here. So here the black curve is the pusher curve, the red curve is the puller curve, and the same bifurcation happens. Okay? So that's something I am again going to explain in the first part of my talk. And this bifurcation comes along with the logarithmic divergence. So this, as I just said, is going to be explained in part 1. But the second more interesting thing is the box size dependence. So that is the tracer diffusivity plot in a simulation box size of 10 swimmer lengths. That's 40 swimmer lengths. And you can see that the red curve grows substantially above what is the dilute theoretical asymptote. Okay, so there's a strong box size dependence, which is indicative of long wavelength fluctuations comparable to the box size. Okay, and here it's even more clear. This is much larger size simulations of almost 1 million swimmers. And you can see that there is this initial bifurcation, which is more or less independent of box size. But then the pusher curve starts to keep increasing with box size. Okay? Now, this is the, if I get to part 2, that's what I want to try and explain. Okay? And that's a signature of collective motion. Okay? So, collective motion is a term for it seems like suspension of swimmers above a certain threshold become unstable to these spontaneous long wavelength fluctuations. Okay? And this seems to be an enhancement due to these long wavelength fluctuations that come in above a certain threshold. Okay? So just to give you a feel, this is a movie from our simulations a few years back, 3 years back. So that's pullers with no collective motion. Okay? And that's pushers. Okay, so you can see that there's large scale sloshing around going on there, which is bound to lead to a magnification of the tracer diffusivity. So I want to come to this in part 2. Okay, so part 1, so remember here we are going to look at the level of a single swimmer or a pair of swimmers, depending on whether we allow for interactions, and argue for what's the tracer diffusivity. And this is the approach followed in traditional suspension mechanics. So I'm going to start with the traditional scenario where I have a suspension of sedimenting spheres. So in this case, they sediment under gravity, there is a force, and therefore each sphere produces a 1/r velocity field. Okay, so to calculate the velocity variance, I'm going to consider a point and add up all these contributions. Each one of them is 1/r, the velocity, so the square of the velocity, which is what matters for the variance, is 1/r squared. And then I add up 1/r squared over 3 dimensions. Okay? So I'm going to assume a random microstructure, so I can just use the velocity and integrate over the volume. When you do that, you immediately see that the volume grows like r cubed, but the square of the velocity only decays like 1/r squared, which implies that the velocity variance actually diverges linearly with system size. Okay? So the larger the volume in which the sedimenting suspension settles in, the higher the velocity fluctuations. Okay, so this was pretty famous. It's the Kalfish-Luke divergence, where Kalfish and Luke found this first in 1985. Okay, and there were a series of articles trying to explain it. Okay? Now, this is important because you can see that the system size dependence, which we observed in simulations for swimmers, comes from the 1/r velocity field. Okay, but if I now go to a suspension of forced dipoles, which is what swimmers are, okay, and I'm going to start from suspension of straight swimmers, which are relevant to simulations. So they go on for very long before tumbling, okay, changing orientation. So I can neglect that change of orientation, assume them to move straight. Now for the velocity variance, I again consider the point x, and then I have these swimmers that I want to add up. Now each swimmer produces a 1/r squared velocity field. So when I add them up, I have the square of 1/r squared, which is 1/r power 4, and then when I integrate over the volume, it's convergent because there are 4 r's in the denominator, only 3 r's as the volume grows. So if I consider independent swimmer contributions, there is no problem. The velocity variance should remain finite. Okay? It appears to diverge at small r, but that's because I've treated it as a point force dipole. But then you can do the calculation and you can show that at dilute non-interacting limit, which should give rise to a term linear in the concentration, that's the finite velocity variance. Okay? And if I multiply that velocity variance by the correlation time, which is the time it takes the swimmer to sweep past the tracer particle moving with speed u, then I just multiply this by L by u, and I get the tracer diffusivity in a suspension of straight swimmers. Okay? So now I could vary the u tau by L. So this is the answer for straight swimmers. As they start to tumble more rapidly, the decorrelation happens faster, the tracer diffusivity goes down. Okay? So that's the answer for a non-interacting suspension, but this is not very interesting. In the Michael Graham simulations, the divergence happened because of the interactions. So that's the next step. So now I'm going to consider swimmers interacting in pairs, okay? And a pair of correlated swimmers contributes to the velocity variance at that point x, okay? So for this, I need to understand how the correlations work. So I consider two of these swimmers. Again, they're straight swimmers. They swim past each other. But the correlation occurs because each one of them has a force dipole velocity field. The velocity field rotates the orientation. So the swimmers were uncorrelated when they were infinitely far apart, but they have been rotated by the velocity field and they're correlated. The amount of correlation is because you rotate the velocity gradient rotating the orientation is 1 by r cubed. Integrated over a distance r, the correlation is 1 by r squared, okay? So, and remember that a given swimmer is surrounded by second swimmers, all kinds of neighboring swimmers, in a three-dimensional volume. Each one of them is correlated by an amount 1 by r squared, okay? So now if I try to calculate the variance, I have the original swimmer contributing a velocity of 1 by r power 4, but that 1 by r power 4 has to be multiplied by the correlation of the second swimmers, integrated over the volume of the cloud, okay? But that's only the cloud surrounding a single swimmer. I have to repeat the calculation for each swimmer surrounded by its own correlation cloud. So there's another volume integral there. So that's the cloud integral, and that's the number of clouds over an infinite three-dimensional domain and a single correlation cloud. And now when I have that, I can count the powers of r. So there are two volumes in the numerator, that's 6 r's, and an r power 4 and an r square in the denominator. So that means that it's loosely speaking dr by r, and that gives you the logarithmic divergence, okay? So if you have a simulation, then you're going to observe something like this. And that's really what Michael Graham had in his simulations, okay? So in a simulations, your divergence is limited by the box size, by periodic boundary conditions. But in real swimmers, if you had really persistent swimmers, run and tumble swimmers, then I would replace L box by the large run length. So that tells me that the velocity variance for very large u tau is going to go logarithmically as u tau by L, okay? So now in this case, for run and tumble swimmers, you can actually solve this for arbitrary u tau by L. So when you do that, you plot the velocity variance as a function of u tau by L. You do recover the obvious linear asymptote for small u tau by L, but then it grows logarithmically for large u tau by L, okay? So the velocity variance grows as log u tau by L for large u tau by L. And the tracer diffusivity diverge at a stronger rate. They are linearly divergent because the velocity variance grows until the bacteria tumbles, okay? And the correlation time is tau, not L by U. So the divergence is linear, okay? And if you can do this for pushers and pullers, then you do observe that the velocity variance is greater for pushers and lesser for pullers. So it's interactions that are responsible for this bifurcation, okay? And the same holds for tracer diffusivities. And so this part here explains that bifurcation that I pointed out in the earlier simulations, the initial box size independent bifurcation, okay? Right. Okay, so now we come to part 2. So in this case, I'm going to be trying to answer the same question based on a different approach, because this will allow me to analyze collective motion, which hopefully I'll come to, okay? So again, we go back to the passive case, okay? So if you now look at the sedimenting suspension from a continuum field approach, then the equations are the Stokes equations here, but with a body force due to the heavy sedimenting particle. So N is the number density field, and that's really a random field for this. It's a fluctuating field with certain specified statistics, okay? So for the case where the suspension has a random microstructure, then I can say that the number density has a certain mean, that's the mean volume fraction of the suspension, but it's completely uncorrelated. So the fluctuations in the number density, I assume, are just a delta function. So the number density at x is not correlated to the one at x prime. And if you assume this is the case, then you use this and write down the ensemble averaged equations, okay? So if you directly average the equations, then you get that the average pressure gradient senses the average body force. So the particles basically renormalize the density, okay? And the flow is therefore driven not by the mean volume fraction, but by the fluctuating number density, okay? So this is what gives rise to the velocity field, and this you can solve, at least given the statistics. So this is easily done in Fourier space. So when you solve this equation, you get an expression for the velocity variance in Fourier space, okay? So remember the velocity variance went like 1 by r in physical space, so the Fourier transform would go like 1 by k squared in 3 dimensions. So that's 1 by k power 4 for 2 of those. And then when you invert it to get the velocity variance in physical space, you are inverting an integral which goes like 1 by k power 4 for small k, with the 3-dimensional Fourier volume going like k cubed, okay? Which means that the divergence occurs at small k. Okay, this is exactly what happened in the earlier microstructural picture, where the divergence happened at large R is now happening at small k. So it's exactly the same thing, okay? And this was first done by John Hinch, okay? And this is a youngish John Hinch in the mid-1980s, a disorder and mixing conference, okay? And this was important because at around that time, the long-range hydrodynamic interactions had been interpreted by Batchelor, and there were renormalizations which took account of the divergent integrals. So when Kalfish and Luke first proposed this, there's always the question of whether it was a question of renormalization and interpreting it correctly. And it was Hinch who showed that there are these Poissonian fluctuations in number density that can't be renormalized away, and the velocity variance will diverge linearly, okay? At the same conference, we had another person. So that's John Brady there in 1988, 3 decades back. But some of us are convinced that John is immune to aging. Those who aren't, that's John's separated by 3 decades. So, and that's the first product of the John School, Don Koch, at the same conference. Yeah, so. Okay. So let's get back to the active case now. So in the passive case, we had sedimenting particles which acted as a fluctuating force, okay? But swimmers are force-free. Remember, they're force dipoles. But we need fluctuations, okay? And we need these fluctuations in position orientation space, because our swimmers are slender. We care about both positions and orientations, okay? So I need to derive fluctuations, and a natural source of fluctuations are tumbles, because the tumbles obey Poisson statistics, but they only occur at a rate, mean rate of tau. There must be fluctuations about that rate, okay? So the idea is now, in the passive case, this is the microscopic number density which fluctuated, the Dirac delta function sitting at the location of the ith particle. So I need to generalize this to phase space. So I account for both position of the swimmer and orientation of the swimmer, and I have my microscopic phase space density, position orientation space density, okay? And then I ask for its evolution. It's going to evolve because both the positions and orientations evolve. The positions evolve due to convection with swim speed and the velocity disturbance field. The orientations evolve because of turning by the velocity gradient. So this is okay. But then there is a source of tumbling, okay? So the tumbling is really an instantaneous large change in orientation that occurs with a certain probability, okay? So here is a bacterium tumbling from the initial orientation Pi to a final orientation PFI, okay? And I have a random variable in front that obeys certain statistics. So the mean of the random variable is delta t by tau. And that's because the way I would implement this is, I would take an interval, small interval, and say that if the random variable falls within a fraction delta t by tau of that interval, then I implement the tumble, else it goes straight, okay? So if I do that, then I have a fluctuating source here. So what I can do is, if I just substitute the average of f, which is delta d by tau, then I get back this equation, which we had already seen. But this equation contains more information because it also contains the fluctuations of that random variable. And therefore, I can actually write this as the equation for the fluctuating probability or the fluctuating phase space density with the noise there. So the noise involves the statistics of this quantity. Okay, so you can do that, and therefore you have what I'm just terming a fluctuating run and tumble equation, okay, with the noise obeying certain statistics. Okay, so we look at the simplest version of this equation where the swimmers execute random tumbles. Okay, so the equation is this. So what I have is, instead of the fluctuating sedimenting suspension of passive particles, now I have a fluctuating bacterial bath with the tumbles constituting a noise source. Okay, so the noise source is delta correlated in space and time, and the orientation correlation looks like this. So it's random tumbles. So what the noise does is it picks out an orientation p at a certain instant, and it does so with uniform probability on the unit sphere. Okay, so I subtract a sink of probability which is uniform on the unit sphere, but a source that is localized, and that must be the case because remember, tumbles don't add or reduce bacteria. So when integrated over orientation space, I shouldn't have a fluctuation in the number density. So it conserves the number. Okay. Okay. So this is really at the base of the continuum field perspective. So I take the fluctuating probability, combine it with the Stokes equations, as I'll tell you, and then I try to extract the tracer diffusivity out of it. So this is the equation for the tracer. Okay, so that the convection diffusion equation, where you can see that if the tracer is Brownian, it's going to diffuse with due to thermal forces, but it's also going to be convected by the velocity field of the fluctuating bacterial bath. Okay, and so what I need to do is I need to calculate this bath velocity field. Now the bath is characterized in principle by the n swimmer probability density, but I'm going to look at the simplest description where I say that there is a mean field approximation where I approximate omega n as omega 1 power n. So the correlator is just given by the average over the noise we just saw. Okay, and the correlation I really need is the pair correlation, which matters for the velocity correlation function and the tracer diffusivity. Okay, so the idea is the following. I calculate omega 1 from the fluctuating run and tumble equation, and then I use omega 1 to calculate the bath velocity field. From the bath velocity field, I use the Green-Kubo relation to go to the diffusivity, and the average involves the average over the statistics of the bacterial bath. Okay? So the question is, why does the bath velocity field care about the fluctuating probability density? That's because of the bacterial stress. Okay, so if I have a bacterial bath, I have the Stokes equations augmented by a term which is the stress due to the bacteria. So if you recall the passive sphere case, spheres acted on by an external force acted like a fluctuating force field. The bacteria, because they are force free, act as a fluctuating stress field. Okay, so that's the stress, and you can see the form in simple terms. So if I could remember, this was the single bacterium which exerted a force along its orientation. The stress is just the first moment of the force. It's really a dipole force density. Okay? Now for slender bodies, X is proportional to P. F, the thrust, is also proportional to P. So I get a PP there, and I have to average that, which is just that. So PP averaged over the bath statistics. Okay? So that stress drives the U bath convects the tracer. Okay? Okay. So now I'm going to do this at two levels. I'll first consider the bacterial bath interaction without momentum coupling. Okay? So by that, what I mean is that there is one term missing here. The probability density is not rotated by the velocity field. Okay? Which means that this becomes a one-way coupled problem. So what I can do is, because omega 1 is independent of U, I can first calculate omega 1, then calculate U bath, and then go to the tracer diffusivity via the Green-Kubo relation, calculate the diffusivity. Okay? Now, this is done so that we make sure the approach gives us the answer that we already know, which we know from the microscale approach. Okay? So this is in principle straightforward. That's just the Stokes equation. So the novel part here comes from solving the bacterial bath. And you can do that, okay? So this is what I just said in equations. So I solve for the bacterial bath dynamics here. From the bacterial bath dynamics, I have the stress, the Fourier transform stress, which gives me the bath velocity field. That bath velocity field, when substituted into the velocity autocorrelation, gives me the tracer, okay? So if I just substitute for this U bath, that's the bath contribution to the diffusivity, which involves, if you notice, the average of 2 of those fluctuating probabilities, okay? Okay, so now I need to do the first step. That's the most difficult step here. And some of these details appear in my students' posters. So in fact, you can solve the bacterial bath dynamics for arbitrary U tau by L, okay? So the idea is, this is what you need to solve. It's an inhomogeneous equation. So you want to convolve the noise with the Green's function which satisfies a localized forcing, okay? So you just generate a localized noise, impulsive forcing, and then convolve it with the noise to get omega 1, okay? So that can be done via a Green's eigenfunction superposition. So the main thing is that the bath modes, so to speak, are of 2 types, okay? There is the discrete mode. This is more intuitive because the discrete mode represents diffusion. So on long wavelengths, the discrete modes describes relaxation of bacterial concentration fluctuations, okay? But there is also a continuous spectrum, which are number density waves. Okay, so as you can see, these are force dipoles aligned in a certain direction, okay, and they swim, and the wave just moves along with the swimming bacteria. Okay, so the Fourier mode here moves along this direction with the swimming speed projected along k, and there are a continuum of these modes with the discrete mode that make up the entire dynamics. Okay, so then you include the continuous spectrum and the discrete mode in the Green's function. And when you do that, you see that the discrete mode doesn't contribute to the concentration fluctuations, to the velocity fluctuations, sorry. It's the continuous spectrum modes that do. If you add up over all the continuous spectrum modes, then you effectively get the same answer that we had at the beginning, okay, from a single tracer swimmer interaction. So the superposition of the continuous spectrum modes adjusts itself to produce a single swimmer beside the tracer at a certain position with a certain orientation, okay? So this is just convince ourselves that this is the right approach, okay? So this is just summarizing it. So this was our microscopic approach, the tracer particle with the swimmer. And then this is the field approach with the swimmer replaced by a fluctuating bacterial bath with a noise source. That fluctuation goes into the velocity covariance, which gives us the tracer diffusivity, and they give us the same answer, okay? Now you can in principle do it with pair interactions, okay? With the bath characterized at the pair level rather than at the singlet level, and you would recover this answer, although we've not done it yet, okay? But the more important thing is to go to collective motion, okay? So the reason we did all this is because the bath approach allows you to now calculate the tracer diffusivity in presence of the collective mode, which appears to lead to a diverging tracer diffusivity beyond a certain threshold, okay? So here the difference is that, so notice that the title of this slide has been with momentum coupling rather than without momentum coupling, and this is a very crucial addition. The addition is this term here, okay? So the noise is generating fluctuations in probability, but the fluctuations in probability are also being rotated by the velocity field that it generates via the stress term. Okay, so that tells you that's two-way coupled. I can't just calculate omega 1, go to U bath, and then go there. I have to calculate the coupled dynamics of this, and once I have that, I can go to U bath and do the same thing. Okay. Okay, so that's the rotation of a given bacterium by the bath velocity field, which is really symptomatic of long-ranged hydrodynamic interactions. Okay. Okay, so before I tell you the final answer, to just get a feel for this, what we'll do is we'll kill the noise, okay, so that I have a deterministic system, and I try to look at what the solution of the Stokes equations coupled to the mean kinetic equation is. Okay? So in other words, I perturb it and do a linear stability analysis. And if you do this, then you find an instability. That is really collective motion at linear order. So you find that a suspension of bacteria is linearly unstable when they are pushers. Okay? And the physical mechanism is not difficult to see. So in the linear stability analysis, you impose a Fourier mode of velocity. So when you have a velocity wave, then the bacteria are rotated by the back velocity wave, and they align along the local extensional axis. Okay, so the extensional axis switches directions as you go around. But because these are pushers, in that orientation, they're going to exert an extensional flow that reinforces the original velocity field. The velocity field grows, the bacteria are further aligned, and the whole thing leads to exponential growth. Okay? And the exponential growth comes in when this response overcomes the viscous damping of the solvent. Okay? So that suggests there is a threshold, and that's the threshold there. So it's a combination of the volume fraction and the persistence parameter. Okay? So when NuL squared exceeds this thing, then you have exponentially growing modes. Okay? So obviously a linear analysis won't work beyond that. So I'm going to be calculating, I'm going to be now adding the noise, okay, which generates, so in the linear stability analysis, you put in a Fourier mode, but now I have the noise doing it for me. So these are continual bath modes that are being generated, the bacteria are being rotated, and the velocity fluctuations grow, and they become more and more long-ranged and dominant as I approach that threshold. Okay? So that's the calculation. Okay? So this is just to, going back to the movie that I showed you, it manifests itself in simulation. So that's a suspension of pullers, and that's a suspension of pushers. And those red trajectories there are the trajectories of tracer particles. Okay? So you can see pullers, they are quite localized. Okay? Whereas pushers, because of these collective sloshing modes, more or less move through the box. Okay? Okay. So the idea again is the same. You have the bath dynamics, John, 2 minutes, and the Stokes equations, but now they are coupled. Okay, so I solve for this, but get omega 1 anyway, okay, and then use the omega 1 in the same formula to calculate the tracer diffusivity and the velocity variance. Okay, so when I do that, the velocity variance diverges as the inverse. So it's 1 by phi minus phi c, if you think of phi as the volume fraction. Okay, the covariance becomes really long-ranged in the vicinity of the threshold, and the tracer diffusivity diverges with an inverse squared singularity. So that's where we are right now with the first version of evidence that collective motion leads to divergent signatures in the tracer diffusivity. Okay, so I would like to end with this. So if you're going to have long wavelength fluctuations on orientation, which become important close to the threshold of collective motion, and if you're going to be shearing them, you're going to be doing work to orient those long wavelength fluctuations. So there has got to be a signature in the viscosity too. So there's going to be tracer diffusivity and viscosity, and hopefully a way to relate them in some sort of a fluctuation dissipation relation. Okay? And this is just, there are analogs of course, so whatever I spoke about in equilibrium systems would be like a second order transition. Okay? So, and the viscosity does exhibit a divergence here, although it's very mild. In colloidal systems where you have a similar critical point, the divergence is actually much stronger, okay, due to hydrodynamic interactions. Okay? So we expect that the signature might be stronger if we believe this, but there are also several differences. Okay? So there is no thermodynamics in our case. So even in the colloid case, the transition has a thermodynamic signature. It's because of the attractive depletion forces, but this is nothing like that. And it's very different in that there is no concentration fluctuation in the linear theory. It's all velocity and orientation. So it's not obvious it would have anything to do with this. Okay? And because there's no thermodynamic signature, I'm not even sure how good a linear theory is. If you go to nonlinear order, maybe there is no divergence, it's something else. And the question is, what's the nature of the ordered phase? Okay, the collective motion phase where there are supposed to be long-range correlations, what does it look like? And the evidence from simulations is that it's still disordered. Okay, so maybe the correlations change character and so on. So these are questions right now we don't have an answer to. We're just starting out doing the first calculation. So with that, I'll end, and I'll be happy to take questions.
Time for some questions. Yes.
Hi. In the slide just before part 2, like there was one of the curves in which the diffusivity was apparently decreasing for one of the cases. Like, could you please explain like what's the physical?
Well, you could say that there is an anti-correlation. So whereas a single puller would act to convect the tracer in a certain manner, the other puller, the correlation is such that the induced velocity is opposite to the direction of the that a single puller would induce, which decreases the diffusivity.
All right, thanks.
Other questions? Prabhu?
Ganesh, you explained the logarithmic divergence of the velocity variance for swimmers that don't tumble very much. Rather, the persistence is large. But in real bacterial systems, the persistence, as you said in the beginning, is of the order of 1 unity. So is that real in real systems? Do you really see a logarithmic divergence in the velocity variance?
No. No, so that particular question was because it was relevant to simulations.
Right.
So most of the simulations that David Saitio and Michael Graham have, if you calculate the box size and the decorrelation time, the swimmers more or less swim through the box before they turn significantly. And so the real swimmers won't.
Okay.
Yeah.
There was another question in the back?
So I think it's following up the previous question. So if you were trying to measure this experimentally, would the log divergence get killed because of a far stronger decay due to wall interactions?
So as I said, in an actual system, U tau by L tends to be small. It's maybe about 5 at most. So that question was relevant to simulations, not so much to real systems.
And more questions for Ganesh? So the experiments haven't seen this, obviously, right?
The log divergence,
yeah,
no.
Right.
Yeah.
Is anyone trying?
Well, there are indirect signatures by Clement and so on, but I hope he is. So,
Okay, great. Are there other questions? Yes. Yes, they have created those.
yeah, they have. You can do that, but they do have an athermal rotary diffusion type fluctuation. So you can't go very far. So it's about
Yeah. You can go quite
that
far.
right?
Yeah, but you can still go 10, 100.
10, 100.
Easily, yeah.
Oh, okay. Okay, I wasn't aware of the 100 thing.
But then you run into the walls, so. Other questions, comments? If not, let's thank our speaker again.